Hey guys. All right, I'm gonna write up a little warm-up exercise here. So let's see. Okay, so yeah, just these four series. This is like exercise 15.4, I think, in the book. So yeah, just have a go at that. Let's give it like 7 minutes, so we can resume at 5:15. Okay, so let's go ahead and go over these. So for the first one, what'd you guys say? All right. Well, I think the first one diverges, right? Uh, obviously the context kind of suggests that we can use the integral test, but actually I think this one you can do it without the integral test just by saying for large n, log of n is less than the square root of n. So square root of n log of n is less than n. So 1 over n log n, or square root of n log n, diverges by comparison to the harmonic series, I believe. You guys agree with that? Hopefully yes. I didn't. Yeah. Okay, great. Yeah. So sometimes, okay, actually I want to kind of talk about this a little bit more in a second. There's a thing that I like to call kind of the growth hierarchy of functions. And so if you know kind of the growth hierarchy, then it's easy to like do stuff like this basically, and deal with like a lot of different functions that way. So you can use it to do stuff with like the comparison test. But of course, some of these, the integral tests will actually be like useful. This one is also like, pretty clearly divergent, since log of n is greater than or equal to 1, right? At least for n greater than 3, or greater than 2. Yeah. I think this one is a pretty good one to actually use the integral test. So if you take f of x equals 1 over x log of x log of x, you can hold on. So the integral from, let's say, I don't know, 4 to infinity. Yeah, really any sufficiently big positive number, because remember, it doesn't actually matter what's happening, for like small values of x. That's not going to affect the convergence of the integral, unless there are like poles, obviously, but there are no poles of the function, which is important, actually. I mean, there shouldn't be any poles if you're going to use the integral test, at least not in the domain of integration here. But if we want to integrate f of x, this is the integral from 4 to infinity of, so we have 1 over x log of x log of x. So there's a substitution we can do. If we put u equals, actually, I think if you do u equals log of x, then, so if u is log of x, then du is going to be log of x over x, right? Or no. It should be, yeah, sorry. It's 1 over x log of x, right? Yeah, dx, right? So then, yeah, that's what's supposed to happen. So this is actually just like 1 over u du, right? So we get the integral from, I don't know, something, whatever. Let's see, log of 4, I guess, to infinity of 1 over u du. Not that it matters, because this is just infinity, right?
Yeah.
So the series should diverge. The integral test. Let's see. Getting a little disorganized. So the integral test tells us that the series diverges. Okay?
Yeah.
Do we not need to prove the function's decreasing, or that's just obvious?
Well, it's decreasing because x, log of x, I mean, well, log is an increasing function, right?
Mm-hmm.
So log of x is also increasing, and then x is, of course, increasing. So if you take 1 over an increasing function, you get a decreasing function.
Yeah.
Yeah, but I mean, it's actually a good exercise to just like, set down that reasoning carefully. But in this case, I would say it's not strictly necessary. Especially since here, it's like everything we're doing with like the integral test is, like I was saying, it's kind of like heuristic, So the point here is really more to like train our intuition, I guess, about what should be happening. But yeah, so what about this one? What did you guys say for this one?
Converge.
Yeah, actually, it should converge. So what did you use to get that?
I said because log of n is less than a square root of n.
Yeah.
Again.
That's probably how I would do it too. Yeah. So log of n is less than the square root of n for a large n. So the comparison to series, we have the comparison to the series of square root of n over n squared, which is 1 over n to the 3/2, and this converges. So the original series converges too. Okay. Anyway, yeah, great. So any questions about this?
Can you go over the growth hierarchy?
Oh, yeah, sure. Okay. Yeah, so this is kind of, I don't know, I think other people use this term too. So this is common functions. So basically, you can kind of classify or sort of order functions that grow by like this. So for instance, you could have like powers of n is a type of function that grows with n, right? So you could have like n to the b for some power b, right? And basically, it's just a fact that like any power of n asymptotically grows much slower than like any exponential function of n, right? So I don't know, x to the n if x is greater than 1, right? Which just means that like no matter how big b is and no matter how close to 1 x might be, eventually if you make n get big enough, this just it sort of outpaces this one, right? And you can kind of like do this with a lot of functions. So for example, any power of log, so log of n to the a, yeah, this is of course for b greater than 0, and this is also for a greater than 0. Any power of log will grow much slower than any power of n, right? And then like x to the n, for example, well, really, it kind of this actually says a lot. And then of course there's like you'd have like, well, yeah, you can have like bounded functions, because of course those just don't grow really, asymptotically, they just stay bounded. And then actually just from this collection of things, you can kind of get a lot of other stuff. Like for example, any exponential function like this is going to asymptotically be much less than like n to the n, right? because actually you can think about this as just like e to the n log of n. And then of course we know that like n log of n grows much faster than n eventually, right? So, so of course this is going to grow a lot faster than this one. So getting used to like being able to sort of figure out what functions are like much bigger or much smaller than other ones will help you a lot in kind of doing very rough-handed estimates and analysis of like series and stuff like that, or just sequences even. And so like, you know, in here, you can also say like, you know, bounded functions are much less than like, you know, log of n to the a, which are much less than like, you know, log of n to the b, you know, so you can kind of like insert things in between. So I guess like I'll just, and that really just follows from the fact that log is asymptotically much less than powers of n, right? So like, yeah, log of n, I guess to the c maybe, goes in between here and like, you know, whatever. I mean, you can just keep adding more and more. I mean, this sort of becomes like an infinite, you know, chain of functions, but, you know, a few sort of basic rules about how these functions compare to each other gives you a way to assess which functions will asymptotically grow much faster than others. Okay, so it's just a useful thing to like get to sort of practice with and internalize, you know, and just be able to immediately recognize, you know, when a function is going to grow faster or slower. Any questions about that? Yeah, I was considering making like a separate video. Now that we've gone over it in the discussion, I'm kind of like on the fence about it. We'll see, you know, how my time shakes out, I guess. But yeah, I mean, I think it's an important part of doing analysis, basically, right? And actually, just to be clear, also like, so you can actually give this like double less than thing kind of a rigorous meaning, which is like, you know, we would say that like f of n is double less than g of n if like the limit as n goes to infinity of f of n over g of n is 0, right? That's kind of what we're saying when we do this. For whenever, if f and g are both positive, if f and g both have to be positive, then this literally means that like for a sufficiently large n, g of n will be not only bigger than f of n, but bigger by any like factor that you want. Like you can find n such that g of n stays greater than like 10 times f of n. You can find n so that g of n stays greater than 100 times f of n or whatever, right? Any multiple actually, you can make g of n be bigger than f of n by that multiple. So yeah, questions? Okay, great. So yeah, that's kind of what I meant by that. It's useful for series and stuff. So here's another problem for you guys. What was it? Hold on. Oh man. Oh, 1 second. For some reason, I thought of this problem just like 10 or 15 minutes ago, and now it's slipping away from me. It had something to do with, oh, right, okay, yeah, I remember. So suppose AN is a series which converges but does not converge absolutely. Let let's say NK be, you know, how do I want to do this? Let NK be, like, let's say like, okay, yeah. ANK be the subsequence of non-negative, I guess, I don't know. Yeah, non-negative terms. So ANK is greater than or equal to 0 for all k. And AMJ is the subsequence of negative terms. So AMJ is less than 0 for all k. So note that like ANK and AMJ are sort of complementary subsequences, right? Like every term AN belongs to exactly one of these two subsequences. Either it's non-negative, in which case it's part of this subsequence, or it's negative, in which case it's part of this subsequence, right? So then the problem is show that the sum from k equals, let's say 1 to infinity. Let's say this is n equals 1 to infinity. Of a and k is positive infinity, and the sum of a and j from j equals 1 to infinity is negative infinity. Okay? So yeah, take about, yeah, let's say 10 minutes. So we can resume at 5:44. And yeah, I'll go ahead and make a little, room if you guys want to talk to each other while you're working on it. Let's see. There we go. So yeah, feel free to talk to each other about it. Hey, all right. So, okay. What I will say about this is that there's sort of what I would call the intuitive idea of why this is true is actually like pretty simple, but sort of like formulating it in a really like precise, formal way is a little bit tricky. Would anyone of you like to sort of like describe the basic idea that you have of like why this should be true without getting bogged down in like notation and stuff like that?
Well, when you add them together, they should converge.
Yeah, yeah. It's basically like, okay, there's some kind of like vague sense in which the original series here is kind of like the sum of these two, right? In some sense. Obviously, that's not really true because if this is infinity and this is minus infinity, you can't actually like add them together and get like a finite value out of that, right? But what you can say is like, okay, imagine if this series converged to like a finite number, right? Uh, then in order for the overall series to converge, this one would also have to converge to some kind of finite number, right? Because if this one was like a finite number and then this was negative infinity, then like if you look at the partial sum, if you sort of look at the partial sums of this, each partial sum of this is like a partial sum of this plus a partial sum of this, right? And if the partial sums here tend to negative infinity and these ones tend to some finite number, then overall adding those two things together will give you something that tends to negative infinity. So this would go to like negative infinity, right? So you can't have like one of them being a finite number and the other one being infinite if this has to converge. But if that's the case, then like, okay, if both of them were finite, right, then what you could say is that actually like when you look at the series of absolute values of an, right, then every partial sum of that is going to be like a partial sum of this minus a partial sum of this one, right? And if both of these tended to finite numbers, then the series of absolute values would also tend to a finite number, which is what we're assuming doesn't happen if we say they don't converge, that this doesn't converge absolutely, right? So that's the gist of like why this is true. Did that make sense? I know I kind of like said a lot of stuff, didn't really write it down, but yeah,
Could
the
you
idea.
please write it down? Because
Okay, sure.
yeah.
I'll try it. Okay, so here, okay, here's the idea. Let's see. Okay, each partial sum of n is the sum of a partial sum of a and k, right? Positive terms. And AMJ negative terms. Okay, so if A and K were finite, but AMJ went to negative infinity, then partial sums like partial sums of AN would tend to negative infinity. Okay, and that's just because each partial sum of AN is the sum of one of these partial sums and one of these partial sums. Okay, so if these ones tended to some finite number, right, and these tended to a negative infinity, then when you add them together, you'd get something that tended to negative infinity. Okay.
Yes.
So this can't happen. So if either, and then there's like there's sort of a mirror argument where it's like, if the sum of A and J were finite and A and K added to positive infinity, then the partial sums here would tend to positive infinity. So basically what I'm saying is that if you assume that the sum of an converges, then either both of these sums are like infinities, or they're both finite numbers. You can't have one and not the other. So if either sum of a and k or sum of a and j is finite, then so is the other one, right? But if they are both finite, then, right, a partial sum, well, oh, oops, sorry. Let's see, then basically the sum of an absolute value converges because the partial sums of this series are differences of, partial sums basically of, like they're differences, I'll just say this, positive terms minus negative terms, right? If you look at a partial sum of the absolute values, right, then all that is it's like whatever the positive terms were in that partial sum, those are unaffected by the absolute value, and all the negative terms in the original partial sum, when you take the absolute value, they get negated, right? So the partial sum, any partial sum of like the sum of absolute values here is just going to be the difference of one of the partial sums of this one and one of the partial sums of this one, right? So if we assume that the partial sums of the positive terms go to a finite number and the partial sums of the negative terms go to a finite number, then clearly the differences between those will also approach a finite number. It'll just approach whatever the difference is between the overall sum of positive terms and the overall sum of negative terms, right?
Yes.
So if both of these sums were finite, that would mean that the series would converge absolutely, okay? But if we're assuming that the series doesn't converge absolutely, that can't happen. So basically between all of these, in all of these situations, we've shown that basically like neither one of these series can be finite, right? Like, because if one of them were finite, then both of them would have to be finite. But then we showed that that's also not possible.
So like a lot of proof by contradictions, like the three,
Yeah,
just eliminate
basically.
every other possibility in it. Okay.
Yeah,
That's
or
cool.
contrapositive if you want to think about it that way.
Oh yeah.
Yeah. But yeah. That's exactly right. Yeah. Yeah, sorry. Maybe I should have maybe suggested, yeah, I need to get better. I need to like remember to sort of give some hints sometimes about like I should have said, consider what happens if one of these is finite, for instance. Like, I don't know. Sorry. Sorry about that. I hope it wasn't too miserable trying to think about this problem. But yeah, like if you want to kind of see just briefly what it would look like to actually formalize this idea, here's literally what I would say. So set Sn to be the nth partial sum, right? So k equals 1 to n of ak. And then let's say like, Tn is the nth partial sum of, I don't know, k equals 1 to n of a and k, right? So these are the positive terms. And like un is, let's use j for this one. Not that it actually matters like what letter you use, right, for the indexing. But yeah, the nth partial sum of the negative terms. Okay. So then, so what we can say is like, okay, suppose this sum is some like, real number, right? So our first goal, right? Remember from here, our first goal is to show that if this is true, then the sum of the negative ones is, the sum of the negative ones is also finite, basically. So we want to show that sum of j equals 1 to infinity amj converges, right? I guess what you can actually just say, you don't actually have to do this one by contrapositive, actually, now that I think about it. I don't think you do, because what you can say is, well, un equals basically, or rather, sorry. No, yeah. Un is like S, something like S M N minus T, let's say TL, where you know, TL is like, or sorry, where L is like the, I guess the maximum of the Ks for which NK is less than MN. Sorry. Yeah, I'm sorry. Maybe there's some better notation here, but so all I'm trying to say, right, is that like a partial sum, like any of the partial sums over here are just like the corresponding partial sum of this one minus all the positive terms that happen to be in that partial sum, right? So I'm just like subtracting out all the positive terms. So this is like, here it's like K, oh yeah, L is, oh right, yeah, that's right, yeah. So L is just sort of like the biggest, you know, it takes us to like the furthest partial, or the furthest positive term that happens in the partial sum SMN, right? So
How did you how did you get the MN for the S term?
Because, so if you look at UN, right, it's the sum of like AMJ. So the last term here is AMN, right? So this is equal to like AM1 plus AM2 plus AMN, right? So if I want to think of this as being like a partial sum over here with some terms deleted, right? The last term here is MN, so I might as well take the MNth partial sum over here, right? And then subtract out all, whichever of those terms happen to be positive, basically. Does that make sense?
Yes.
Yeah. Okay. So that's what this is. And it doesn't even, the thing is like, this doesn't really matter. The point is just that like, all that really matters in the end is that like UN is equal to some S something minus a T something, basically, right? That's actually all that really matters. You know, I'm just like sort of laying it all out very explicitly, but all that really matters is that each UN is a difference like this. And that as N increases, this and this both increase to infinity, basically. So so then as N goes to infinity, Mn goes to infinity, oops, and L goes to infinity. So UN approaches whatever this is. So sum of K equals 1 to infinity AK minus S. Okay. So what we've shown is if is finite, then so is the sum of the AMJs. Right? That's what we just showed. Okay? So that's like, that's that's this part. That's what we just did. Okay? So then what you can say is, you know, so now suppose that the sum of the positive ones, and actually maybe it would have been better to call this S and then call this T or something. I don't know, it doesn't matter. So suppose that the ANKs sum to T and the AMJs sum to U. Okay. So then we can show, what we want to show is that the sum of the absolute values of AN from n equals 1 to infinity converges. And that's actually a very similar thing, because basically it's like if we set Sn equal to sum of n equals 1 to infinity, or sorry, not, what am I doing? Not n and not infinity. So like, let's say k equals 1 to n of the absolute value of ak, then Sn is like, basically it's going to be, let's say T something minus U something, where and now I need to figure out what these somethings are. Not that it really matters, but right, it's going to be like let's say T TP minus UQ, where P is like the maximum K such that NK is less than N, or sorry, less than or equal to, I guess. And Q is the maximum J such that MJ is less than or equal to N, right? So as N approaches infinity, then in this expression here, P approaches infinity and Q approaches infinity as well. So if TP goes to T and UQ goes to U, then Sn goes to T minus U, right? So what we showed is, from this we would conclude converges absolutely. Okay. And so if we were assuming initially, right, that this series does not converge absolutely, then that's impossible, right? So yeah, I know this business here is probably hard to digest, or maybe like it doesn't seem obvious. And honestly, like this is probably more, it's more like hairy than it needs to be, like notationally, you know, things don't like this. I would say, honestly, if someone wrote this argument here, that like as like their submission for like a homework or a test problem or something, if someone just like wrote this down, they would get almost all of the credit, if not all of it, because this really encapsulates, encapsulates the, oh my God. Encapsulates the heart of the argument, basically. Yeah. So anyway, any questions about that?
In the one that you wrote more formally, do you need to do like, is that enough, or do you then need to do like another case where then they're like both, or they're not both positive infinity? Or wait.
So
never mind, that doesn't make that much sense. Never mind.
Yeah, okay, yeah. Yeah, because basically, if either one of these is not going to converge, like, okay, if the sum of the positive terms doesn't converge, then it has to diverge to plus infinity. And if the sum of the negative terms doesn't converge. It has to
Right.
diverge to negative infinity. Yeah. So there's only really, and so there is technically like one case I kind of left out, which was like over here, I showed that like if the positive terms sum to a finite thing, then the negative terms do. But I didn't show that like if the negative terms sum to a finite thing, then the positive terms do. But that one is just like literally like a mirror. It's like a mirror image of this argument, basically. So I kind of left it out for that reason. But like technically that's part of it too. Basically, you're showing that like one of these two sums is finite if and only if the other one is. Okay, one of these two, I guess.
Got it.
Yeah, I know it's like complicated. I don't know, but the idea is really like not that complicated. I think the main benefit of doing this, okay, is to avoid making mistakes like people will do something. I've seen in general, like I've seen people do a lot of stuff with this where it's like, for some reason, if you take like the sum of positive terms is the positive terms, and then this is like the negative terms, and then like the, let's say like tn are the partial sums here, and then like un are the partial sums here, they would say like something like Sn is like Tn plus Un or something like that, where like Sn is the partial sum of the overall thing, right? And so like, I don't know why this just happens a lot. And it's just not true, right? Because it's like, we don't know, basically the whole point of like having to take these subsequences and stuff is that you don't know like what the, you don't know like what the pattern of pluses and minuses is. You know, it could be like plus, minus, 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 plus, plus, minus, minus, et cetera, right? Like the pluses and minuses could be distributed just like randomly, right? So then it's like here, it would be like honestly, actually just toying around with like a really random looking sequence like this will really help you understand like exactly what all of this notation is really doing, about being careful. All it's doing is being careful about like how you describe a partial sum, right? A partial sum of the original series of an as like a sum or a difference. I guess here, since we have the absolute value, it's a difference. But in the original thing, right, we said that a partial sum of an, right, is just the sum of a partial sum of here and a partial sum from here, right? But it's like the way that that's actually true is a little bit complicated because you don't know how many terms to take from here and how many terms to take from here to get the overall partial sum, basically, right? Although here I did it in a little bit of a flipped way where I was saying like a partial sum of this thing is the difference of a partial sum from here and from here, but it's the same principle, which is that like, you don't really know explicitly like how many of the terms in this like mnth partial sum from here, you don't actually know how many of the terms are positive. Yeah. Actually, wait. Whoa. Actually, no, you kind of do, right? Because if there are n terms, oh yeah. L actually, you can actually write a formula kind of here. Okay, that's funny. You can just say like, here you can just say this is like mn minus n. Because there are n terms in this one. I didn't think about that before. There are n terms in this one, so the rest of them have to be positive, basically, right? There are mn terms in the overall thing, and n of them are negative, so the rest of them are positive. So, okay, that does simplify this a little bit too. Yeah.
Hold on, now I'm a little bit confused about how many terms there are. Are there n terms or are there n terms?
Right, so there are n terms in un, right? Because there's just one for each value of j going from 1 to n, right? But in Smn, right, you're letting k go from 1 to mn. So this is like here, it's like this. Right, so this is like AM1 plus AM2 plus AMN.
Is n just mj?
This is n terms. No, n is literally just a number here. Yeah. And then j is like the index inside of this that goes from 1 to n, right? So there are n terms here, and then this is like a1 plus a2 plus a3 plus amn. So there are mn terms here, right? So all I'm saying is that, you know, the rest of, you know, if there are like n of these terms, these are just some of the terms from here, and there are n of them, and those are all of the negative terms in this sum. So then the rest of them have to be positive. So basically you just take the first mn minus n terms of the positive sum, and you get all of the positive terms that are in this. Okay?
So is mn larger than n?
Yeah, it has to be, because mn is actually a, you know, I mean, smn is like a subsequence. Yeah. Uh-huh.
Okay, I get it.
Yeah.
Okay.
Yep. Yeah, it's like, you just have to get practice like thinking about subsequences and stuff. The nested indices really can mess with people's minds. And I know the feeling. I mean, I know the feeling of like it being this like hard thing to digest, but you'll get used to it eventually. But yeah, anyway, so here there actually is, I guess this claim may warrant like a sentence of justification, right? The only reason this, I mean, the reason this has to hold is that if this didn't hold, that would basically mean that there was only a finite number of positive terms in the entire original series, which obviously is impossible. So, yeah. Yeah. Well, I guess, yeah. Okay. Maybe that would warrant its own separate argument. Like, so technically, I guess technically over here, somewhere inside, we would want to show that there is an infinite number of both types of terms. But I think that's really not too hard to do. It's just a similar thing where it's like, if there, I mean, yeah. If there was only a finite number of one type, then that would mean that the sum of all of the other ones, the infinitely many other terms, would have to be finite for the whole thing to converge. And then you run into the exact same issue as over here, where it would end up converging absolutely if that happened. Okay, anyway, all right. I've said enough about this problem. Probably made it more complicated than it had to be. But so that'll be all for today. Thank you guys for coming. I actually think, so in spite of how like complicated this problem is, it is actually like an important problem, I will say. Like this result, this fact about conditionally convergent series is something that you should be aware of, I guess. Because it'll help you like with your sort of mental model of how conditionally convergent series look. I think this is like, for me at least, it's like an important part of the picture of like how I imagine conditionally convergent series, I guess. Okay. So anyway, that's all. I'll see you guys. I have office hours tomorrow, so if you come to that, I'll see you then. Other than that, I'll see you next week.
Thank you, Professor. See you.
Okay, thank you.
Yep, bye-bye.